This is AP Physics, assignment from Chapter 28, problems dealing with Kirchhoff's laws. I'm trying a little bit different format of going over the homework on this one, so give me feedback and let me know if you like this better. So, problem number 21. We've got a circuit there. We've got 3 different branches shown. Okay, and we want to find the currents in each of the different branches. So then looking at your batteries, you got a 12 volt and a 4 volt battery. 12 volt battery is going to dominate. Okay, so then I'm specifying I1 traveling along this branch, just emphasizing a little more on that side. And I2 following what the 4 volt battery wants to do. I have I2 going up this middle branch. I3 then coming around the other side, going from here all the way around to there. Now, if you did not specify your currents the same way, that's no problem. Okay, your math will be a little bit different, but you'll come up with the same answers. I'm going to make sure that that is clear, that that is an I2. So then we've got our 3 currents. Now, that means looking at our 3 different lines, I1 and I2 come together right here at this junction. And then I3 comes out of the junction. So then based on the way I've drawn the currents, I1 plus I2 will equal out to I3, or join together to form I3. Okay. On the 2 loop rule equations, I'm starting at the upper left-hand corner and going counterclockwise on each of these. So on the left-hand loop, if I start there at the pink dot I just put, I go down the first side through the 8 ohm resistor, and going through that 8 ohm resistor, we're in the direction that current has been denoted. Current always flows from high to low potential, so that would be a negative I times R, so that would be a negative 8I3. Okay, I round the corner, I get to the junction at the bottom, then I go up the center branch, and going up the center branch, I go from the negative terminal to the positive terminal of the battery, which would be an increase. So in my second equation there, the second term is a positive 4 volts. Continuing across that second one, I go up through the 1 ohm and the 5 ohm. They're in series. I just combine them to be a 6. We're moving up that center branch in the direction the current flows. And so then that would be a minus 6 times I2, and then that's equal to 0. On your right-hand loop, again, starting at the upper left-hand corner where I have the black dot, okay, going down the center branch, I would go through the 6 or the 5 and the 1, moving downward, so I'm opposite the direction of I2, so that would be an increase of IR, so that would be a positive 6I2. And then moving down, I would go from the positive to the negative terminal of the battery, so that would be a negative 4. Rounding the corner from the bottom junction going right, I go to the 12 volt battery from the negative to the positive, so that's an increase plus 12. And then I go through the 1 and the 3 that are in series, so I'm combining them to be a 4. And I'm going in the direction of I1, so that would be a minus 4I1. So you've got the 3 equations there with those signs. Again, if you specified I1, I2, I3 on different branches or in different directions, you should still get the same or equivalent equations. Maybe the signs are flipped or some of your I's are changed, but they are equivalent equations. Now, from there, do algebra to solve down. So I've shown the algebra here to be able to solve down for the 3 different currents. Again, it's shorter to plug those into your calculator and solve the system of equations, but either way is fine. So if you want to look at the algebra, you can. Part B, we're calculating the energy for each battery. Okay, on each battery, energy would be power times time, and power is V times I, and V times I think is probably the easiest equation that we can use of the three power equations. And so in part B, you end up with energy as V times I times T. So then I'm just taking the voltages of the two batteries, the current that is flowing through that given branch that the battery is in, and then the time period was 2 minutes, so multiplying by 120 seconds. Part C, the energy by each resistor. On this one, I'm using the same idea, but now I'm using the power equation I squared times R. And the reason being is you're going from resistor to resistor, and you know the resistance values, but you haven't figured out what the voltage values are. So that turns out to be the easiest equation here. So then it's just a matter of plugging the current in that's in the given branch where the resistor is, and the resistance and the time period. So you can see the algebra on that one. On D, different types of energy transformations. 12-volt battery, you've got chemical potential energy. Some of its loss is heat in terms of internal resistance in the battery, but most of that energy goes into energy dissipated in those resistors. And if they're ideal batteries, then it all goes into energy dissipated by those resistors. Part E, change in internal energy in terms of the batteries. That's just a matter of taking all the energy values that we calculated above for the resistors in part C and adding those values up. Problem number 23. You know in this one that the current goes going across the center branch through the ammeter is 2 amps. So then we can use the loop rule to solve down for I1 and I2. Knowing the center branch current, then there's no substitution. It's just a matter of setting up the equation and then solving down. So then if we know the current is going to the right through the center branch, then I1 would be all of that there, and I2 would be the current through all of this right here. So then solving for I1, I would set up an equation for the top loop. I'm starting right there at the black dot going across the center branch. So that would be in the direction of I2. So I times R would be a negative 2 times 5 ohms. Then I go to the junction on the right side in the middle and up following I1, the red current, and I get to the 15 ohm or 15 volt battery from negative to positive. That's a positive 15 volts. Moving then through the 7 ohm resistor in the direction of the current. So that's a negative 7 I1. And then do the algebra to solve down. For I2, okay, I can use the loop rule, but because I know what I1 is already, I can solve down for I2 just using a junction rule. I1 and I2 go into the junction on the left side where the black dot is, and 2 amps comes out. Plug in your I1 value, plug in 2 amps, and solve down for I2. C, the EMF of your unknown battery down there. Now you do have to set up a loop rule equation on the bottom loop there. So then I'm starting again at the black dot, and I'm going to go clockwise around that lower loop. So that would be I2 times 2 ohms and going across the center, that should be a negative. And then when I get to the EMF of the battery, I'm going from low to high, so that would be a positive. And then when I get to the 2 ohm resistor, I'm in the direction of the current, so that would be a negative. So I changed the signs there to reflect going in a clockwise direction, but either equation is equivalent. And then do the algebra to solve down for the missing EMF. Number 3, thinking a little bit backwards here, they've given you the equations, and you want to set up, you want to draw in part A what that circuit would be. First thing I notice in this one is you have an I2 in both of your loop rule equations. If you have an I2 in both loop rule equations, okay, that I2 is going to be along the center branch. So I'm going to put, just kind of notes here, I1 on the top branch, I2 on the middle branch, and I3 on the bottom branch. Okay, now kind of setting up from where we are, I'm going to draw just a generic circuit with two loops, and then I'm going to erase and add things in. Okay, so looking at the top equation that we were given, we've got a negative I1 times 220 ohms. So I'm going to make a spot there, and I'm going to add in a resistor. So that would be a 220 ohm resistor, and based on the negative sign, I'm going to draw the direction that I want this current to flow. I'm going to have my current I1 move around the branch in that direction. Okay, so then continuing to move on across, the next thing I run into is a positive 5.8 volts. So I'm going to make another little spot here, and I'm going to put a battery in here so that I'm facing to get a positive. So if I go from the right side to the left, the 220 would be a negative IR, and negative terminal to positive terminal, that would be a positive 5.8. Now I need to go down to the center branch and put in a 370 ohm resistor. So I'm going to take out a little chunk there, put in a resistor here of 370 ohms, specify the direction of I2. In the equation, I need I2, it'd be a negative I2 times 370. So doing the loop rule across here, I would need that I2 going toward the right. Now, I'm going to the second equation. It's a positive I2 times 370. So on that one, I'm going to start at this point right here where I just put the pink dot. And if I go counterclockwise from there, I'll be going opposite the I2 denoted current direction. So that would be a positive I2 times 370 is shown in the middle equation. And then I'm going to need to add my next resistor here. So then the next term in the equation is a positive I3 times 150 ohms. So I'm going to erase a little spot here. I'm going to put a resistor in there in the bottom branch. I'm going to label that 150 ohms. And now if I'm going counterclockwise, which would be from my neon green dot there down and around. Okay, oops, got to choose a different color. Okay, so I'm going down, and then I would be going across the bottom branch to the right. I need that I3 150 term to be a positive. So I'm going to specify my I3 in this direction. So then as I move around that lower loop, then the middle term in my second equation will be positive. Now the last thing I have in that middle equation is a battery. So I'll make a space for a battery. And I need that battery so that I'm going around to have a negative 3.1 volts. So that means I'm going to start with the high potential terminal and go to the low. So I go from high to low, and then in the equation, that would be a 3.1 volts is a negative. So in the diagram that you drew, you should have something that is equivalent to what I've drawn there. Now, in part B, you're solving down. Plug it into your calculator, solve the system of equations down, or I've shown basically what the value or what the math is in the substitutions if you choose to do it algebraically. So then it asks you to explain the meaning of the values that you got. I1, 11 milliamps. That's what's going to be flowing through that top branch where the red is, going around counterclockwise from the pink dot to the green dot. I2, 9.13 milliamps. It's going to be going from left to right across the middle branch. Okay, and then I3, negative 1.9 milliamps. Well, the negative means the way that we denoted the current on the diagram is opposite to the way it is actually flowing. So then it would be starting at the green dot, flowing through the lower branch around to the pink dot, going in what would be a counterclockwise direction. Problem number 29. Same idea as the other ones, using Kirchhoff's laws. You're setting up what the currents are in each branch and being able to solve down. So emphasizing a little bit more the current directions I've drawn. The 24-volt battery is your highest voltage battery. And so I have I1 going around this branch in that clockwise direction. I've chosen to draw I2 across the middle branch from left to right. And then I've drawn I3 around the lower branch going in a clockwise direction. Again, if you chose different, it's fine. Your equations will be equivalent. So from there, setting up the equations, you get a bolder color. Okay, junction rule. On the junction on the left side, right there where the pink dot is, I've got I3 coming into that junction from the bottom, and then I2 and I1 exit it. That means I1 plus I2 has to be equal to I3. Then, if we do the loop rule, doing the top loop, starting from our bright green dot, and going around in a clockwise direction. Won't use that color green again. And so I'll go across the battery, load a high, positive 24 volts, cross the resistor in the direction of I1. So that will be a negative 28 times I1. Then we round down to the middle branch. We're going backwards against the current, and so my IR for the 12 ohm resistor will be positive 12 I2. And then we go from high to low on the battery, so that's a negative 12 volts, and that's equal to 0. On then the lower loop, down, skip a line, so I'm down on the fourth line on the work. On the lower loop, I'm starting at the pink dot and going around clockwise. So that'll be negative to positive terminal on the 12-volt battery, positive 12 volts in the direction across the 12 ohm resistor. So that'll be negative IR, negative 12 I2. Down the far side, and we get to the 16 ohm resistor in the direction of I3. So that'll be a negative 16 I3, and then the total is 0. From there, plug it into your calculator and solve, or you can see the algebra there to be done to solve down for your missing currents. Part B, you're calculating the power on each. It's a matter of an I squared times R because we know the I's and we know the R's, so you can see the algebra for that one. Number 31, same process. Okay, looking at our batteries, 12-volt battery, highest voltage battery. So then I'm going to let that determine I1, and I1 would be pushed around in that clockwise direction. I'm calling the center branch there I3, and I'm going to push across here toward the left. And then I2 being pushed across the lower or around the lower branch. And so all of that would be I2. So then in terms of junctions, let's see, At the junction over on the left side where I'm putting the pink dot, I2 goes into the junction and I3 goes into the junction, and I1 comes out. So I1 would equal I2 plus I3. Now applying the loop rule. Okay, on the loop rule, I'm going to start right up there at the upper left corner and go around in a clockwise direction. I'm going in the direction of I1, which means high to low potential across the 2 ohm resistor, so that'll be a negative 2I1 using V equals IR. And then the 4 ohm resistor, same idea, negative 4I1. You could have combined those immediately into one term because they're in series on the same branch. And then we go across the center branch. The only thing there is your 3 ohm resistor, and we're in the direction of I3, so that would be a negative 3I3. And then we go up the left-hand branch from the pink dot to the purple dot, and that is going in from low to high on the battery, so that would be a positive 24 volts. So then this equation is the equation for the top loop, and then a line of some algebra. And then right here we go to the bottom loop. So in the bottom loop, I'm starting over there at the pink dot, going around in a clockwise direction. So I go to the 3 ohm resistor in the middle branch, and we're going against the direction of current, so I times R would be a 3I3. And then we hit the junction on the right side and go down the right branch to the 1 ohm and the 5 ohm resistor. Both of those were moving around in that clockwise direction. So then in the direction of the current, those will both be negative. So negative 1I2, and then the 5 ohm, negative 5I2. And then we hit the 12 volt battery from low to high, so that'd be a positive 12. And that is equal to 0. So then you have your 3 equations: loop rule or junction rule equation, loop rule equation, loop rule equation. And then it's basically algebra I've shown to solve down for the values, or plug it into your calculator and solve the system of equations down. So you should be comfortable using Kirchhoff's laws to be able to set up systems and solve